Today we'll be presenting the presentation, Graph Problems and Their Applications. It will be presented by William Baires, Nicholas Barron, and Casey Cannon. So, a graph is a data structure that consists of a set of vertices and a set of edges which may connect the vertices. The reason that we include the quote here, "A good drawing is worth more than a long lecture," is because to visually represent these nodes and edges is easier than to articulate them verbally. So here we are able to see that we have nodes 0, 1, 2, 3, and 4, and the various connections between them, the edges here. So we can see that there's a connection between 0 and 1, as well as a connection between 0 and 2, but there's no direct connection between 0 and 3, or 0 and 4. There's variations in graphs. Not all graphs are the same. Some graphs are undirected, which means that the connections are, in a sense, unidirectional or bidirectional. They can go either way. In a directed graph, there are more constraints. Some connections can be one-directional, while others can be bidirectional. It's also worth mentioning that in some undirected or directed graphs, there can be floating vertices that do not have any connections at all, but are still related to the graph in some way in which they need to be represented as a node. There are also the instances of weighted graphs as seen by the example on the far right. In this case, each edge has a numerical value associated with it, its weight. The weight doesn't necessarily have to be a weight, while it can be. The weight can also be a distance between 2 points or a cost that it may cost to ship something between those 2 points. The weights are just additional data points that can be used as constraints in algorithms. So now we'll be quickly going over a couple different ways to store methods when we represent them in code. So there are two main ways to most commonly store a graph. One is an adjacency list. We use a list, like a linked list, that contains connections to different nodes in the array based on the edges that are connecting them. So you can see in this example that 0 has a connection to 1, 0 also has a connection to 3, and 0 has a connection to 8, as represented by this list representation here. The other most common way to store a graph is with an adjacency matrix. An adjacency matrix is a matrix, of course, where the nodes are represented by two columns the nodes are represented by a row of nodes and a column of nodes. And anytime there is a 0, it represents a connection between two nodes, and anytime there is a 1, it represents a connection between the nodes. A 0 represents no connection between the nodes. A 1 represents a connection between the nodes. So according to this graph, for the same representation, we can see in the column of 0 that there is a connection to 1, also a connection to 3, and a connection to 8. So this is also a valid way of storing the matrix, of storing the graph, but of course there's going to be pros and cons to doing either. So the list contains a space complexity of the amount of vertices plus the amount of edges. It's better for sparse amounts of connections because when there's less connections, the list is less bulky. It's faster to add and delete nodes as compared to an adjacency matrix. It's also faster to iterate all the edges. Adding edges in both circumstances is a constant of 1, though, to keep in mind, or is a constant time complexity. For the adjacency matrix, it is vertices squared is the memory used in the worst case. It is slow to iterate all the edges because you cannot simply go through them quite as directly as in a list. Adding edges is constant, just like in the adjacency list, but because of the nature of the matrix, it's faster to search this list.
In general is to organize data. Search algorithms are actually what make that data accessible. Two of the central pillars that I'll be talking about within search algorithms are the breadth first search and the depth first search. As you can see, it's not limited to just these two algorithms. There's also Dijkstra's algorithm, great at finding the shortest paths. And within depth first search, there's even more variants of it, such as best first and the A-star search. Before we get into the actual algorithms of depth first search and breadth first search, I thought it was a good idea for everyone to look at visualization of the algorithms and see if you can figure out what the difference is between both of these search algorithms. Now, they essentially do the same thing. They are traversing a tree or a graph, but they do it in quite different directions. So, just looking at those visuals, notice how breadth first search, how it differs in its traversal to the depth first search. Let's first start exploring these algorithms with the breadth first search. Here we have an algorithmic description, pseudocode on the left, visual on the right. Looking at the pseudocode, you can quickly see that a queue is actually used to implement BFS. We'll be looking at that in detail on the next slide. On the right, we have a visual. Different than the last one we just saw on the previous slide, this is using a graph instead of a tree. But the concept is the same. We have to have some kind of starting node or root node. In this case, that starting node is that one right there. That's totally arbitrary. It could be any node in this graph. Here it's 1. So the first nodes that are explored in a BFS is actually the ones that follow the level order. If you've ever done a level order traversal, then you know this very well. So those nodes that are one level away from that one node right here are the ones that are going to be first explored. So that's the 2, the 3, the 4, and the 5. Those are the first level away, that first degree of separation. Now, if we look at the second level, that's going to be the next few nodes that are going to be explored by BFS. So what are the next few nodes? Well, those are the ones with 2 degrees of separation, such as the 6. Another one is 7, and last but not least has to be 8. Those are all the nodes at 2 degrees of separation, or in that second level. BFS will continue until it reaches the lowest level. In this case, there's only 2. Let's go ahead and look at the next slide. So here we have another example, and we're actually going to look at how a queue can actually implement BFS and give us the correct order that we're looking for. So let's first look at the pseudocode, and we can see that the first step is to set all the nodes to not visited. Because we are just starting the search, of course, none of these nodes should be visited. So that's an important first step. Next thing in the pseudocode, we need to initialize and construct our queue. Here on the visualization, we have our queue ready to be loaded up with some nodes. Next on the pseudocode, we have queue NQ, the initial node. So I need an initial node to add to my queue, right to the front of that line. Just like we said before, it's totally arbitrary where we start. For this example, we're going to make that A the initial node. So NQ tells us that we're going to throw that initial node A to the front of our queue. Next up on the pseudocode, it says while queue is not empty, well, our queue is certainly not empty because we already know it has our initial node A. We're going to do the following. So it says node equal to queue.dq. So node is going to be an important variable holding on to the current node that we're looking at. So node is going to be equal to queue.dq means we're going to take A away. We're going to remove it from the front of the queue, and we're going to assign it to node here. So we're going to keep track of that. So if node has not been visited, well, how can I tell if it's been visited? We're actually going to keep track of which nodes have been visited, which ones haven't, using this visited array. Right here it says order of discovery, meaning that's the order in which we're exploring these nodes, that level order, that BFS we're going to do. So if node has not been visited, well, A is certainly not in our visited array yet, but now it should be because we just explored it. So we're going to set that equal to true, meaning we're going to throw that node A inside this array. Next on the pseudocode, it says for every edge connecting that node to a neighbor. So the edge is going to tell us where our neighbors are at. So we're currently looking at that initial node A, which edges connect it to its neighbors. So this edge connects it to B and G, meaning that B and G are going to be neighbors. So let's see, what are we going to do with these neighbors? Well, it says if the neighbor has not been visited, well, certainly these neighbors are not in our visited array. They're not in our queue yet, so we haven't been there yet. We're going to NQ them, throw them into our queue. So front of the queue, I'm going to throw B if I'm going for alphabetical order, and then G next up on that queue. So because we just finished that iteration, we're going to go all the way back to the beginning of the while loop and repeat the process with our new front of the queue. So let me erase that A because that one's already gone. Let's take away these labels. Coming back to the beginning of the while loop, we're going to see, well, Q is not empty. We're going to do the following again. So Q is certainly not empty. It's got 2 nodes in there. So that means we're going to point our current node here to the top of the queue and also eliminate that from the queue. So at the top of the queue, we have B. We're going to dequeue it from our queue, and we're going to throw it here in our current node. So B is now our current node. We're going to explore those neighbors of B. So if B has not been visited, well, it's certainly been visited now because it's our node. We're going to throw it in our visited list. So now it's the second node in our order of discovery. Now all over again, we're going to look at the edges to see which neighbors belong to B. This is going to be the second degree of separation, that second layer. So if B is our node here, well, it's connected to C, so this is a neighbor. And G is also a neighbor. Well, if the neighbor hasn't been visited, we're going to enqueue that neighbor into our queue. Let's look at C because we're going from left to right. So C has certainly not been visited, not in our order of discovery, and it's not in our queue. So we're going to throw it right after G. So we'll repeat the process over and over again, always assigning the current node to the top of the queue. I'll leave the rest of this BFS to you guys, but I'll go ahead and show you the solution in the next slide. So go ahead and give it a try on your own and see if you do get the solution. So here's the solution to that graph from the previous example. So if you did your BFS correctly, this is the order of discovery you should have gotten. Now let's take a look at some real-world applications of graph theory and their search algorithms. So for BFS specifically, I was able to find some really relevant and some really cool applications. So for BFS, you'll actually see its use in social media and in search engines. In my research, I found that BFS is actually hugely important to these massive social media companies. If, for example, they wanted to look at their broad network, their entire network of users, they could run a breadth first search to look at everyone in that network. The same goes for a smaller network. Say we're just looking at the mutual friends between two nodes. We can run a BFS to get all those friends lists. So this is a visual of what one of these social networks might look like if we drew it as a graph. And if we wanted to do that nth level friends, those mutual friends, we could take any two users like this. And if we're looking for mutual friends, right, we're probably looking at those within 1 degree of separation. So we create a list of all those users who are close friends with our users. And all those intersections between those friends, for example, this user right here, both have a close link to that person, will show up in that mutual friend list. So anytime we're on Facebook, we're seeing those mutual friends lists, we're seeing BFS and graphs in action. Looking further at the utility of BFS in social media, similar to that mutual friends list that we were just talking about, that nth level connection statistic can actually be really useful for creating friend suggestions. So maybe that friend isn't on your mutual friends list. Maybe there are 2 degrees of separation. That person might show up as a suggested friend. A really cool fact that I found out in my research was how small a world these networks are. They're actually called small world networks for that reason. After running a shortest path distance on all the users in the Facebook network, Facebook actually found out that there's an average of only 4.74 people between any 2 Facebook users. So any user on the earth, doesn't matter where they're from, on average will only have 5 friends between any other user in the world. Let's now take a look at depth first search and its algorithm. Here's the algorithmic description of depth first search. We have the pseudocode on the left and a visual graph on the right. As you can see in the pseudocode, a stack is now used for the implementation of DFS. So that's first where they differ to BFS. And on the visual, we can actually start to see some of the search differences. So DFS will actually explore a branch down to the furthest level before exploring any other branches. So if you notice, it goes 1 to 6 before going to 7. So rather than going one level at a time, it's actually going one branch at a time, one direction at a time. After it completes or reaches the end of that branch, it'll go on to the next one, and then the next one, and then so forth. So it's actually doing the same thing as BFS that has the same goal of just traversing the graph, but it just does it in a different direction. So here, just like we had with BFS, is the same example for implementing this time a stack. So we're going to use the same initial node, A, but this time we're going to run a DFS. So if we look at the pseudocode, first we need to make sure that all nodes are set to unvisited. So our visited array down here is empty. We create our stack here, our stack structure, and we're going to push that initial node this time to the bottom of the stack. Let's go ahead and jump into the while loop now. So it says, well, the stack is not empty. We're going to do the following. So the stack is definitely not empty. It's got my A node in there. We're going to pop the stack and assign that to our node. So if I pop the stack, I eliminate the top of the stack and assign it to that current node. So now that I have this current node A, I'm going to check a few things. Well, has it been visited? Now it has, so we got to update that to true. And then for every edge connecting it to another node, we're going to label those nodes a neighbor. So B is a neighbor and G is a neighbor. Next on the pseudocode, it says if the neighbor has not been visited, we're going to push that neighbor onto the stack. Now, just like choosing an initial node is arbitrary, the order at which you push these nodes onto the stack is also arbitrary. So depending on the order you decide on, that might change the specific order of discovery you get here for a DFS. Now, for my example, I'll be going reverse alphabetical pushing, but you can go, leftmost, rightmost, doesn't matter what you choose as far as order goes. So I'll go ahead and skip to the solution on the next slide. Go ahead and give it a try on your own. Just make sure you're following those reverse alphabetical pushes so you get that same order of discovery as I do on the next slide. So here's that solution if you follow that reverse order pushing. If you followed a different order, then you probably got a different answer. So let's go ahead and look back at that first example of BFS and DFS on a tree. So now, hopefully, after covering those algorithmic descriptions, we have a better idea of how these are different. So BFS, as we talked about before, you start with your initial node and you explore the entire level of nodes. So one level at a time, going deeper and deeper. Now BFS also goes one level at a time, but it doesn't explore all the nodes in that level. It explores one branch, so going deeper and deeper into the branch until it reaches the end, and then it'll go to the next branch. And once it reaches the end, it'll make sure it covers any other sub branches here. And as we saw in the pseudocode, right, another big difference, right, is the structures we can use to implement these searches. So DFS will be using the stack, and then BFS will be using the queue. Let's take a look at how DFS is useful in mapping routes. So take a look at the map. We have our place of origin, we have Dortmund here, A, and our destination, Hamburg, B. Now, how can DFS be useful? Well, first we have to look at how can this be turned into a graph. If we separate this into those grids, each one of these squares in the grid could represent a node. This could be 1-1. For example, this could be 2-4. And so what DFS will help us do, it's going to map a bunch of routes from A to B by using that algorithm that we covered. So it's going to find that, hey, maybe I could go through here to get to B. I could also go through here to get to B. So it's going to help populate all those different routes, and that'll help us choose maybe which one's the most fuel efficient, or which one's the fastest, which one's the shortest amount of time, which one doesn't go through toll roads, right? DFS is going to be helpful in giving us all those possibilities. DFS in maze solving is actually really similar to that routing example we just saw. We have a start and end destination, and we have a grid of squares, possible paths. So DFS, what it's going to do is going to go depth first. It's going to try to get as far away from that start point as possible. Maybe it'll end up here. It'll try those different paths. It might have to backtrack. But in the end, if there is a possible path, DFS will find it. Just like we saw with the previous example, that maze could be always turned into a graph. Just like we saw in that previous example, the maze can be abstracted into a graph, and that's going to help DFS run its exploration of those nodes. Just like we saw in the previous example, DFS is all about abstracting it to a graph first. So those grids can be abstracted to nodes, and then using those nodes, we can find that possible path. Where can these nodes, where, just like we saw in the previous example, the first step with DFS is to abstract the problem into a graph. So we had our grid right here of squares. Now it's a grid of nodes. And then these links right here tell us, hey, we can go from this square to the next. And as you can see by the green links right here, the green edges, that is the solution.
So now I will talk about the topological sort, which is a very interesting algorithm because it takes a directed acyclic graph of, say, dependencies. If you're installing, say, an npm package which defines a set of dependencies, or if you're installing, say, a Linux package which defines a set of dependencies that it needs. But your installer can only do things linearly. That is, it must install item A, then item B, and then item C. So, what you can do, what the algorithm, what topological sort allows computers to do, is take the nodes and is take this graph of dependencies and effectively linearize it, make it so that this graph will be built bottom up in the correct order. The complexity of this algorithm is roughly the number of nodes plus the number of vertices plus the number of edges. So it's not too complex. However, with rather full graphs, it will be quite a challenge. Now, a rather interesting implementation of this is the tsort utility that POSIX defined. This was used in older versions of linkers in order for the linker to just need to install dependencies in a correct order. However, now that linkers tend to do this internally, tsort has been less used. Additionally, this can be viewed as scheduling when you only can do one running job. That is, say there is a job F, which must be run before the job E, and so on. This allows the scheduling algorithm to run as many things, to always have something to do, as long as there's no cycle. So to discuss the implementation of topological sort, you first take, there are two common implementations. You have depth first search, which is a depth first search based one, which first checks for cycles, then does a depth first search until there is no possible next node. Because we know that it doesn't have cycles, we can say that depth first search will always end up in some terminal node. So then, once we find that node, we add that result node to our list and remove it from the graph. We do another depth first search until eventually we run out. Now this is a very intuitive implementation, but it does have a high overhead, needing to do a depth first search every time. An alternative is Kahn's algorithm, which starts with a list of terminals instead of just trying to find them. Effectively, you ask the graph what is its list of terminals, and it should be able to find them. But graphs that do not nodes that do not point to any other node. So in the example here on the slide, nodes D and F would be terminal because they do not point to any other nodes. And you would take that list of terminals, add it on, and then remove them from the graph, repeating this procedure so that would be linear in the number of nodes and linear in the number of edges. Now, graph coloring, the simple act of taking a particular graph, usually undirected, and coloring each node so that it is different from all its neighbors, is apparently a very hard problem to do. So, as you can see, it is known to be NP complete for any color above 2, for any number of colors above 2. The 0 and 1 colorings are rather trivial because because in those cases the number of nodes must be the same as the number of colors, and the 2 coloring is the same as a bipartite check, effectively saying can this graph be split into 2 pieces and into 2 halves, one that's all colored color A and the other that's colored color B. This is known to be squared in the number of vertices. Now, there is a shortcut that seems to have cropped up in around the 90s, which is planarity. Planarity is the notion that you can take a graph and draw it on a plane, so on a piece of paper, where the edges only intersect at the nodes. Now, if you know a graph to be planar, which can be checked in linear in linear time, you can always four-color it. This is due to the four-color theorem, and that is known to be colorable in squared in the number of vertices time. So effectively, if the graph is planar, you only have to worry about the square of the number of vertices. If it's non-planar, however, it can be much more complicated. So the reason this application is that graph coloring is very useful is because you can find there's two applications that we can see. The first is register allocation in compilers, taking a source program and coloring it. There, you map the variables to each node. You map interference between those variables to edges, and you map how many registers there are to the number of colors. Now, in the case that the coloring fails, you can use spillover code to assign variables to memory. And you can also use it for a broader you can use graph coloring for a broader scheduling algorithm. That is, you can say that each node is a job, each conflict between jobs is an edge, and the number of simultaneously running jobs are the number of colors. And in that case, if you cannot color the given graph, you have to start removing edges or removing nodes or adding more colors. So to give an example of the register allocation, we have to define what is the term interference. The term interference, at least in the paper cited previously, is that A interferes with B is the same as saying A is alive at the definition of B. Now, what does it mean for a variable to be alive? Well, a variable is alive if at some particular point, if there's at least one possible axis of that variable after that point. For example, take a look at the iterative Fibonacci function on the right side of the slide. You can see that the variable A is alive at the definition of B because it will be used after it inside the while loop. Even though it may not actually be used, because the while loop the internals of the while loop may not execute, if say n were to be 1, but the possibility is still there. And remember, we are doing static analysis, so we have to assume that if it's possible, it will happen. So compilers tend to not use actual raw source code internally. They use intermediate representations. As you can see here, the Fibonacci loop function has been unrolled into an intermediate containing about 3 labels and 9 different temporaries. You'll notice that there's these things called phi nodes, that there's phi instructions. Phi instructions say, based on where we came from, where was the jump just before our arrival, so we look 2 jumps back, and we say, well, based on what that jump is, we determine what our value is. So for example, the value of T4 depends on where we came from. It is either the value of T7 if we came from L3, or it is the value of T0 if we came from L1. The reason this is used is because compilers like to use static single assignment, which says that there is one assignment to a value through the entire program. Here, all these internal temporaries mean that we can use the rule about aliveness much easier because we can just look at variable names. Now, you'll notice the graph in the right which is the value, which is an interference graph. It maps each value and its interference, as previously specified. So, for example, t11 does not interfere with any other value. Why? Because it is down towards the end of the function where only itself is used. As you'll notice that t0 and t2 interfere with each other, but nothing else. So t0 interferes with t2 because t0 is used in the definition of t4, which is after the definition of t2. Thus, t0 interferes with t2. The other nodes, the values t4 through t9, all have a complex interference graph, but you'll notice that certain nodes do not interfere with each other. So, for example, t4 and t9 do not interfere because t9 is down towards the bottom of that block of instructions and uses t4, but since t4 is never used after that point, it is fine that those values don't interfere. t6 and t8 also have similar values, because you'll notice that t6 is used by t8, but not after the definition. You could imagine that each definition has a point right after it before the next definition starts, and that's where we're checking from. Same thing with t5 and t8. Those two do not interfere, because t5 is used at t8, but not after it. Given this complex graph, we can see that it's not planar, but we can start assigning colors to it. We can use, say, a backtracking algorithm or a branch and bound algorithm. But generally, we will find that this is, again, an NP-complete problem, so it is known to be not in P. You will see that I have provided one example coloring, where one register, color 1, holds 4 values. This is akin to a value in a register being unused at some point in the program, and then the compiler reusing that register for something else. This is accurate behavior. You'll notice that some registers are only used once. Now this is, again, a possible coloring so a compiler may reorder these with a different value. Additionally, a compiler could just assign each temporary its own register. So there are multiple solutions to this, and this one example isn't necessarily the best example.
Now we will be going over the maximum flow problem and solution. There are several various flow problems that can be solved using graphs, such as minimum cost flow, but the most common and the one that we're going to talk about today is maximum flow. So very quickly, we're just going to go through some terms based on this diagram that I've created here. This is a basic first step of a maximum flow problem. You can see that we have capacity and flow. These are the sort of weights on our edges for this graph. The first number is the capacity, so that's how much can fit along this edge. And the second number is the flow. The flow is going to come in handy when we go over our algorithm to solve maximum flow in a couple minutes. Otherwise, you can see that more standout features of this graph would be the source on the left. The source is denoted by having no inward-facing edges, so all of the edges from the source are outward. This is how we know that it is the beginning of our flow graph. You'll also see here that the edges are marked also as arcs or edges. That's because when discussing maximum flow, the edges are sometimes referred to as arcs interchangeably. So it's just something to be aware of when looking at these problems. Then you'll also see at the end here of our graph, there's a sink. The sink is sort of the inverse of the source. The sink has only incoming edges and no outcoming edges. That's how we know that it is where all of the flow is draining off. You'll also see that we have a total flow. The total flow at the beginning of the algorithm is 0. Right now, nothing is flowing through our system, and we've not tested what the capacity of this particular system is. So, why do we use maximum flow algorithms? The most obvious solution is to the problem of maintaining flow through a transport system. So let's say an aqueduct system that needs to get a certain amount of water to different areas of a town. and has different resources to get that water and different methods that it can travel. There's also the motive of airline scheduling. So this is scheduling planes that have flights and gates and making sure that there is enough room for an airline that is coming in and enough room for an airplane that is leaving. There's also the baseball elimination problem. This is a really unique problem because before the age of algorithmically solving the baseball elimination problem, newspapers and other reporting agencies would try to sometimes publish when a team in a major league was knocked out of the league or unable to win. And sometimes these calculations would be incorrect because baseball elimination in a season is really deceptive. There's a lot of dependencies on other teams winning certain games, etc. So maximum flow has some really interesting applications beyond just the flow of liquid. Right now we're going to go over the Ford-Fulkerson algorithm. It's a very straightforward and well-used algorithm. It has a couple steps when going through the graph. We're just going to quickly go over the steps, and then I'm going to go through using a diagram to walk through an example of Ford-Fulkerson and how it can be used to find the most amount that can be transported through the system in the previous slides that we discussed. So first, we find an augmenting path using either depth first search or breadth first search to find nodes. Ford-Fulkerson algorithm is considered a greedy algorithm. So part of the first round of steps is just finding a path, any path. Next, once we find that augmenting path, we will calculate the capacity of that path. Then we will update the arcs and the total flow. The way that we find that capacity, we're going to go over in the next chart. And the way that we update the flows is also called augmentation. So we're just going to go through path by path, putting in as much fluid as we possibly can, and then we're going to do a little trick called backwards pathing to find the optimal amount. It's also worth noting that this problem is considered weakly NP-complete, so we know NP-completeness to mean that there is a non-deterministic polynomial solution to the algorithm. We actually have a somewhat polynomial algorithm here. It runs in pseudo-polynomial time. We basically can't guarantee that the algorithm will be polynomial, but having something pseudo-polynomial is better than having nothing polynomial at all. So the way it's calculated is with a breadth first search, that should be an S here. A breadth first search that is of linear time by the flow of the volume. So let's move on to the next example. So we're going to start with just our graph here. It is the same graph that we had in the previous example. We have no flow going through, but we have some pipelines with capacities. You can see that the most capacity is with this first, or with this last edge coming off of 0, there's a capacity of 9, and the least capacity for this edge 0 is 5. So we're going to start by finding our first path. So let's just pick a path. The first path is truly arbitrary, so I'm just picking one here based on one that I like. We'll go with the least path to start. We'll go 0 to 2, 2 to 3, 3 to 4. So this number 5 here that we picked as our flow, it might look arbitrary, but there's a special way that we're calculating it. All that we're trying to do is we're trying to find the minimum flow through this particular path. And if we follow this path, we'll see that the path begins with a 5 capacity, continues with a 5 capacity, and then continues with a 9 capacity. So realistically, the most that we could fit through this path at any time is 5. That's why, for now, we will add the total flow. We calculate that capacity like in the previous slide. The calculated minimum capacity is 5 for this path, so the total flow is 5, and we'll add a flow value of 5 to every flow that is included in this path. Then we will find the next path. The next path that was found, again, the paths are arbitrary. It's greedy. It wants to find any that it can. The next path that we're picking out arbitrarily is 0 to 1 and 1 to 4. So the capacity, as you can see, there was no flow in these previously, and the minimum capacity that can pass through is 7 because the edge here can handle 7, the edge here can handle 8. So the minimum capacity is going to be 7. We're going to add the minimum capacity to augment the chart, which means we add the flows to 7, wherever they were. And we're going to add the 7 to the total flow. So the total flow is now 15, the total flow is now 12. 7 plus 5, 12. Okay, so this is where we get into the interesting part of the algorithm. Now we're looking for another path through the system. The two paths that we've looked through previously are now at maximum capacity. We can't put any more liquid or data or whatever is coming through. No more can go through either of these paths. So we're going to do a last path. The path that we're going to pick is 0 to 3, 3 to 2. Note that we're doing a backwards edge here. I'm going to talk about that in a minute. 2 to 1, and 1 to 4. This is a path. It does break the rules of our graph by going backwards along an edge. When we do a backwards move, we will be removing flow from the move. So in the case that this here, which was 5, 5 before we found our next path, was 5, 0, if there was nothing flowing through, we could not do a backwards move because a backwards move requires removing flow from that edge. So again, I'll go through our third path. We start with the first bottom edge. It is the only one with capacity. We can't do this edge to 1. We can't do this edge to 2. We have to do this edge to 3. So we'll follow the path 1, 0 to 3 to 2 to 1 to 4. And we'll notice that the flow, the most that could fit through, is only 1. That's because this last path over here was 8 through 7. So if we move along, we can take only one more can fit down this path. So we will add 1 to the first edge. We're moving backwards along a backwards edge, so this goes from 5, 5 to 5, 4. We're taking one flow point away. We're moving back up, adding 1. This edge was 3, 0, so we're adding a flow to that capacity. 3, 1. And then we're taking that last edge, 1 to 4, and adding the last flow. So we'll add 1 to the total flow. The total flow is now 13. So there's a little more room to fit more numbers through. Our last path is the more straightforward path. You could probably see it previously, but there's 4 spaces left. This was 9, 5. It is now 9, 9. We know our minimum capacity is going to be 4. The 4 is going to flow through here and add to 5. So now our edge 0 to 3 is 9 and 5. And the final edge is 9, 9. It is at full capacity and the sink. And reaching the sink, then we add 4 to our flow. So now we go from 13 to 17. You can see that the outward edges are near full. They're not quite full, but the receiving edges are full. So from now, there are no more valid paths to get to the end of the system. This is an augmented path condition. Once there's no path that is available that leads to the end, in this case our capacities are full, then that represents the end of the algorithm. We can conclude that the total flow here is 17. If this algorithm seems weird and seems arbitrary and backpathing seems random to find the solution, that is how I felt as well, but you'll find that no matter what order of paths that you take through the system, if you're filling the minimum capacity and following the rules of backpathing, you will always end up with a total flow of 17 for this particular example. And now we'll be getting into our matching terms. So the matching problem is a problem that handles a bipartite graph, which is a graph with vertices that can be separated into two disjoint sets. This means that an edge may not connect two vertices that are in the same set. So you really just picture a set of vertices on the left and a set of vertices on the right. No vertices on the left may match another vertice on the left. So all of the nodes in a bipartite graph will make connections going from one set to the other, basically crossing. A matching, it's not called a match in terms of matching problems, it's called a matching, is a set of edges that do not share a common vertex. So a matching could be a set of one edge. It can be one edge that shares no similar nodes. It can be 20 edges that all contain nodes that do not share any common vertex. A maximum matching is a matching that contains the possible amount of edges for a bipartite graph. This is going to become more clear when we do the matching problem in a couple minutes when we're looking at a bipartite graph. And similar to the maximum flow problem, this problem is solved by finding augmenting paths. And augmenting paths, in order to find them and in order to designate the beginning and end of a function or of a matching problem, is by finding these augmenting paths based on the conditions. So to find augmenting paths for matching, the path must begin at an unmatched vertex, it must end at another unmatched vertex, and the edges must alternate between being in the matching and not being in the matching. That's a little confusing, but we're going to go through it in a couple of examples. For the next example, though, we're just going to be identifying what a matching is, because it can be a little bit overwhelming when you're just learning about what a bipartite graph is. So you can see here on this slide, there's an example. We have 3 bipartite graphs. They contain the same edges, and we're going to identify matchings versus not matchings in this bipartite graph. So you can see on the left here, we have a matching. It is denoted by the red line on top. The match is from 0 to 1, and you can see that in our selected matching, there is no shared vertice. In the next center diagram, you can see that when we add the edge 1 to 4 to the quote-unquote matching that we had previously, it becomes not a matching because now the edges share a common vertex. At this point, this is just a set of edges. It's not a matching. Now you can see here at the end, we have a maximum matching. As far as this graph goes, the most amount of edges that you could have in our matching are there. There are 3 edges, and you can see none of the edges are sharing a common vertex. They're all using vertexes that do not have any other connections that are in our matching. You can see there's still a connection between 0 and 1, but it's not included in our matching. So therefore, it's not breaking any of the conditions of the maximum matching. So why would we use matching problems? Matching is used for more intuitive solutions. So for matchmaking websites that recommend matches, we use a matching algorithm. Sometimes there are more conditions to a match. A matching problem doesn't necessarily have to have the rule of just not sharing common vertexes. There can also be some logic in when we make matching connections. So sometimes the matchings may have more optimal problems, but don't fit in with our additional logic in our problems. So not every, a dating site might not greedily match. There's going to be some standards that the dating service provides. There's also a way to find optimizations in transportation problems by matching. You can use matching for network flow algorithms. It's very important. And then you can also use matching has been used to match patients to health plans based on residency. So now we're going to go through the most common algorithm for matching, the Hopcroft-Karp algorithm. Hopcroft-Karp algorithm, similar to the maximum flow, finds augmenting paths in the matching, and then goes back through and very interestingly creates a tree in order to augment the graph to find the ideal matchings. So let's go through that. So here we have our bipartite graph. We are using A through C for the set on the left, and 1 through 3 for the set on the right. And you'll see at the bottom we have a key. These are some of our conditions for this particular matching. A cannot match to 1, 2, and 3. It can only have a connection between 1 and 2. We cannot make a connection between 1 and 3. That is the constraints of this matching problem. You can see for B and for C that none of the left-hand nodes can connect to all of the right-hand nodes, and vice versa. We'll start with unmatched vertices, and we will first greedily find any matches that we can using augmenting paths. So we start with the match A goes to 1. That is something that we know we can do. B goes to 3, as we can see as part of our key here. And then C, unable to go to 1 and 3, remains unmatched. So here we have a matching, but is it the maximum matching? We don't know. Now let's do the steps to find the maximum matching. So the way that we find a maximum matching is we start with an unmatched node right here. We'll start with node C, and then we're going to construct a graph based on the existing bipartite graph. So this graph, which is somewhat, I called it a tree earlier, it branches a little bit like a tree. We start with the unmatched node, and we make a connection between each of the nodes that it could be connected to. So 1 and 3, right here. They're matched nodes, and you can see the black line means that there is not a connection between C and 1 and C and 3 for now, but it is a matched node. Next we'll go to 1. We'll see from 1 can connect to A. 1 is connected to A, so we'll continue with that connection. We'll connect 1 and A. We have a red edge, which means that the edge does already exist. Then A, from A we can see in the key that A could also connect to 2. And from there we're now ending at an unmatched node. So let's go back to C. We'll see from 2 there's not really anywhere else we can go. It's unmatched. There's no other links. So back again to C, we'll go to 3, which is the next node underneath C for our right-hand graph. It is matched. 3 is matched. 3 contains a connection to B, therefore we have a red line, and B does not contain a connection to 2, although B is allowed to contain a connection to 2. So we create the black line here, which shows that there is a connection that can be made but has not been made. And then it ends on the unmatched node. When we reach the unmatched node, we consider that the end of our augmented path. So 2 of our paths are contained here on the right-hand graph now. Now we will do a little bit of fanciness where we will start with our unmatched node at the bottom, and then we'll greedily find a path back to another unmatched node. So we'll see that if 2 follows the path to A, follows the path to 1, and follows the path to C, that's a successful path from an unmatched node to another unmatched node. So we're going to depict that down here as 2-A equals -1-C. And you'll see I'm making connections using dashes and equal signs, but just keep in mind, like the black and red lines, this is representing connections that do not yet exist and connections that do exist. So we have the connection between 2 and A not existing, the connection between A and 1 existing, and the connection between 1 and C also not yet existing. And then we will remove that path from the graph. Once we find a path, we remove it from the right-hand graph. There are no more unmatched vertices in this right-hand graph. If there were, we'd continue making paths and we'd continue making these little denotations down here. And once we're done with the right-hand graph, which in this case we are, we're going to augment our graph based on the path that we found from the graph that we already made. We're going to augment our bipartite graph with this 2A1C path. We're going to create the connection between A and 2. We're going to remove the connection between A and 1, and we're going to add the connection between 1 and C. And you'll see when we make these changes of the path based on that we found, that suddenly the graph is now a matching. You'll see that A and 2 have the connection like we talked about, A and 1, that connection is removed because it already existed, and now 1 and C is added as a connection. You can see with this sort of, again, similar to a maximum flow, it does some unexpected things and kind of appears with a solution. So Hopcroft Carp is similarly impressive at finding these matchings, and this kind of algorithm can be applied to solve other problems.
That concludes the presentation on graph problems and their applications.